Hi Rockridge, this is Mrs. Berger, and today we are going through day 3 of our unit on polynomials. Today we're going to discuss 3 different theorems to help us get some answers to things that we might ask about polynomials. So if you remember last time, we used the factor theorem and synthetic division to get us to factors and roots of a polynomial, and we'll continue to do things along those lines. So let's start with a discussion about the remainder theorem. The remainder theorem says if a polynomial is divided by a factor, let's call that factor x minus c, then the remainder of that division problem equals p of c, or entering c into that polynomial. Okay? And so this is fairly useful. It'll help us graph some things, and let's show you how that works out. So first we're going to find the remainder when we divide this quadratic by this linear. And then we're going to use that information to answer the question, what does this tell us about the polynomial at x equal to 1? Okay, so remember, x minus 1, that's x minus c, and x equal 1, or inputting 1 into the function, is what we're being asked. So first, let's find out what the remainder is. We know how to do that. That's a division problem. We're going to use synthetic division because long division's not our favorite, right? So we'll use synthetic division. We're going to find out where this thing lives when divided by x minus 1. We have everything in power order and nobody is missing, so our setup is 1, 9, and negative 16. Bring the 1 down, multiply up, add down, multiply up, add down. Now, the final of this is 1x plus 10 and a remainder of negative 6. The remainder of negative 6, because of the remainder theorem, means that when we put 1 into the problem, the output will be negative 6. That's what the remainder theorem tells us. If you were to divide by the factor x minus 1 and get a remainder of negative 6, then if you had put 1 into that original polynomial, you'll get negative 6. And you can certainly test this. You can replace x with 1 in all of these locations, and notice that negative 6 is what spits out of there. Even more useful information is that when we plot this graph, when we plot this parabola here, we will actually have a graph that goes through the point 1, negative 6. So there is a point 1, negative 6 on the graph p of x. Because if you put 1 in, you get negative 6 out. So that's a little piece of information. You know how we love graphing through points that we know about. We can find the zeros, we can find the vertex, and now we can find this additional point, 1 comma negative 6 is a super useful point that we can use to graph as well. Let's take a look at the next example. We'll use that same skill set. So now instead of a parabola, we have a cubic, a little more difficult to deal with. We want to find what happens when you input negative 3 into there, and we're going to use the remainder theorem to figure that out. So if we're directly putting negative 3 in there, we don't have to convert like we did up here. We don't have to convert from the factor. They just gave us negative 3. So we put negative 3 in there. We'll grab the coefficients, so 1, negative 7. Notice that the linear is missing, so we have a 0 and a 4. Let's pull that negative 3 out of there. So pull the 1 down, multiply up, add down, multiply up, add down, multiply up, add down. And notice that the negative 86 is your remainder. So that means on the graph of p of x, the point negative 3 comma negative 86 exists. Or any other way, any other English words you want to use to describe that. So negative 3, negative 86 exists on this graph. That is the remainder theorem, and that's one point that you can use to help yourselves graph these. Okay? Now let's switch to our next theorem of the day, the rational root theorem. The rational root theorem says if you have a polynomial that has integer coefficients, and that's all we're dealing with in this unit, right? Integer coefficients. No 1/2 x squared or 3/7 y squared or 3/7 x to the third. Nothing like that. Just all nice integer coefficients. That means every rational zero for that function is p over q, where p are factors of the constant term and q are factors of the leading coefficient. That's a lot of words to describe what we're about to do. But what the rational root theorem says is, if there's any way that you want to know what rational roots are on there, you can start with this list of things that are the possibles. Here's what we do here are the steps to find the possible rational roots of a given function. Find all of the factors, all of the numbers that multiply to your leading coefficient and your constant, right? So remember, our leading coefficient, that's this thing, and our constant, that's this thing. Make sure that everything's in power order before you start this, of course. So we want to find all the numbers that multiply to those two numbers. And we're going to call all the numbers that multiply to the constant, we're going to call that p. P goes with the constant. And all the numbers that go to the leading coefficient, q. Q goes with the leading coefficient. So all the choices for p are, what are all the things that multiply to 12? 1 and 12, 2 and 6, 3 and 4, all of those, right? Those are all the things. And then all the things that multiply to q, well, q is just 1, right? It's just this invisible 1. All the things that multiply to q are just 1 times 1, right? So just 1. The rational root theorem says all the possible rational roots or rational zeros of this particular cubic that we're looking at are all the different combinations of p over q. So p over q, and we can shorthand this, so all the positive and negatives of 1 over 1, and now let's go ahead and put these in order, right? 1 over 1, 2 over 1, 3, 4, 6, and 12. The positive and negative versions of those. Because you could have, to multiply to 12, you could have -1 times -12, right? So we want to account for all the positives and negatives, and this is just a little shorthand for that. And you're wondering, why in the world would I want to know all the possible rational roots? You're only ever asking me, Mrs. Berger, what are the roots, right? Well, this can narrow it down, because a lot of times we'll start with a polynomial of a really high degree, and we're trying so desperately to get down to a quadratic that we want to be able to work with, because we've got tools for quadratics. If you want to narrow the field of choices down and try to start with, well, what could they possibly be, or what could they not possibly be, this theorem helps you narrow down your choices to the rational roots. Okay, the rational roots. Remember what rational numbers are versus irrational. We're not talking about square root of 14 or square root of 3. We're not going to get to those types of roots with this theorem. We're just going to get the possible rational roots with this theorem. And then we can use some other tools to narrow down out of these possibles what are the real ones possibly. So p over q is a list of your possible rational roots. Anytime you encounter a question on a quiz or test that asks for the possible rational roots, you should think, oh, they're asking for p over q. And to find all the things of p, all the possibilities of p, I look at the constant and think of all the numbers that multiply to that. If I think of q, look at the leading coefficient and think of all the numbers that multiply to that. If you need to, if you have not finished taking notes, go ahead and pause the video and take these, because I need to clear some space to go through question number 4. So go ahead and grab these notes. Pause if you have to. I'm going to clear the board and show the possible rational roots for question number 4. So this polynomial has a leading coefficient of 2, so that's where q is going to come from. And it has a constant of -6, so that's where p is going to come from. So the p factors are coming from there, and the q factors are coming from there. I'm going to start off by just throwing my plus and minus out front to just to get rid of and take care of that. So all the things that multiply to 6 go on top. So 1 times 6, 2 times 3, and that's about all I have, right? 1, 2, 3, and 6. Those are all the factors of 6 that exist. And on the bottom, I have things that multiply to 2 really only have 1 times 2 as the factors of that, right? So now what are all the combinations? All the combinations include, let's start with all the top numbers over top of 1. So let's start with 1 over 1. I'm going to do plus minus. There we go. So 1 over 1, 2 over 1, 3 over 1, 6 over 1. Now I'm going to take a look at all the different things over top of 2. 1 over 2, 2 over 2, I've already done 2 over 2, right? That's the same thing as 1, so I don't need to rewrite that. 3 over 2, that's new. 6 over 2, have I already written that? Yes, I've already written 6 over 2. I've written 3 already. So those are all the possible rational roots that I could possibly have as roots to this particular polynomial. I'm not saying these are all the roots. I'm not saying these are all the rational roots. I'm saying these are all the possible rational roots. So if this thing has any rational roots, it's going to be something on this list. 1, positive 1, negative 1, positive 2, negative 2, positive 3, negative 3, and so forth. Okay? And 1/2 and 3/2 are additionally on that list. Okay? So if any time you are asked for the possible rational roots, you do this P over Q work, and you'll get down to that list. Now remember, these are only the possibilities. You have to keep going with some other tools that we have to see what are the zeros of the function. Okay? Alright, the next theorem we will talk about is one of my very favorites, and that is the fundamental theorem of algebra, or FTA, the fundamental theorem of algebra. And this seems like the most reasonable one to me. It says if you have a polynomial that has a particular degree, and let's call that degree n, so it has a particular degree n. If you have a polynomial that's degree n, as long as its degree is bigger than 0, then that equation, when you set that polynomial equal to 0, it has at least one solution in the set of complex numbers. So it has at least one solution, and also the number of solutions it has is equal to the degree. So in a little more example-like terms, if you have a degree 4 polynomial, that means you have 4 solutions. If you have a degree 3 polynomial, you have 3 solutions. All solutions, okay? And so on and so forth. Whatever the degree is, as long as it's not a degree of 0, whatever the degree is, that's how many solutions are in that particular polynomial when you set it equal to 0. So the examples we have here, we're asked to find the number of solutions and then use our calculator to find the nature of those solutions. So let's recall what we meant about nature, right? Let's pretend like we were talking about just parabolas. Remember when we had a parabola that cut through the axis twice? We had 2 solutions and they were both real, right? They were both real rationals. But then we had a parabola that maybe it floated above the axis or floated underneath the axis. Now remember what we said about those roots. We said that they were imaginary. And so we are going to take a look at these graphs and figure out the nature of all the different roots. Okay? So first of all, let's write down how many roots we're expecting, how many solutions. So for number 5, what's the degree of the polynomial? Hopefully you said the degree is 3. Therefore you have 3 solutions. And before I graph that one, let's just real quick talk about number 6 over here. On number 6, what's our degree? The degree is 4. And so we have 4 solutions. Okay? So now that I know how many solutions I'm expecting, I can take a look at my calculator and go see how many of those are real and how many of them are imaginary. So go ahead and grab your graphing calculator, pause the video if you need to, and grab your graphing calculator, and I will load my calculator here so I can show you what we're doing. Okay, so in your calculator, what I want you to do is put these two problems in at the same time. So I put, as the first function, I put the question number 5, x cubed minus 3x squared plus 6. And that'll show up on our graph as the blue graph. And then for the other graph, the x to the 4th minus 6x cubed and so forth, that will show up on my graph as red. So if you haven't done this yet, pause the video and enter that into your calculator, and then follow along as I show you what our calculator will help us see. Okay, so now I'm going to look at the graph. So first let me look at the blue graph. That's question number 5. The blue graph is question number 5. I'm going to ignore the red one for right now. And let's see what our calculator says about the blue graph. Now, remember what we said about this question, question number 5. We said that question number 5 has 3 solutions. On the blue graph, how many solutions do we see? We see 1 right here on the x-axis, and then the rest of the blue graph does not interact at all with the x-axis. So what we can conclude from that is we see 1 real 0, this little cut through right here, 1 real 0 right here at the x-axis. And if there are 3 zeros total on this graph, 2 of them must be complex imaginary. Okay, so that's how we use our graph on our graphing calculator to determine the nature of our roots. So we'll go back and declare that 1 real 0, sometimes we can list where that real 0 is. We can go look at the x-axis and tell you where it is. And then the other 2 are complex imaginary zeros. Okay, and that's how we used our graphing calculator to determine the nature of the roots. Now let's switch over to our red graph. Let's go back and look at what graphed in the red. Remember, we were looking for 4 total solutions. And if we look at the red graph, we see it interact with the x-axis in 1, 2, 3, 4 places. So out of the 4 solutions that we knew were in this polynomial, all 4 are real. All 4 of them were located at the x-axis, so those are all real. So just as a reminder, real roots encountered at the x-axis, complex imaginary, don't cross or bounce at the x-axis. Okay, and you already know what total number you have based on the degree, so you can always just subtract the real from the total and you'll get the imaginary. Okay, so that's the fundamental theorem of algebra. Now, we are going to, on a couple of very intense problems, so if you need a brain break, now's a good time. On a couple of very intense problems, we are going to take all of these theorems and put them to work. Okay, so if you've already taken your brain break, let's get going. On question number 7, we are going to find all of the real zeros of this function. Not all the possible rationals, not all the, nothing else. We are going to find the zeros of this function. And we're going to write our answers in exact form. So if we have to encounter anything that's got, radicals or anything, we're going to simplify those radicals. We're not going to have decimals. So here are the steps we're going to do. First of all, we're going to list the possibilities so that we can narrow down the field of options. So remember, the possibilities, those are found by P over Q, right? So we're going to list our possibles, P over Q. So P over Q for us is positive and negative. Now we have to think of all the different things that multiply to P. So that's 1 and 20, 2 and 10, 4 and 5. I think that's it, right? Yeah. So 1, 2, 4, 5, 10, and 20. And all the things that multiply to Q, well, Q is just 1, so that's just 1. And I'm not even going to really bother rewriting these because we can all see that positive and negative 1, 2, 4, 5, 10, and 20 are my possible rational reals. So now I'm going to look at the graph. I'm going to go graph this in my graphing calculator, and I'm going to see if I can see any of these numbers at the axis so that I can have a place to start with. Okay? So I'm going to go look at the graph, and you can pause the video and put this function into your graphing calculator and see if you notice positive or negative 1, positive or negative 2, positive negative 4, positive negative 5, and so on. See if you see any of those rational roots on your graph. Alright, hopefully you had time to enter that into your calculator. We put that in y equals as it was given to us, and then we take a look at the graph and we see if we can notice anything. Now, was anything on our list noticed at the axis? Well, a bunch of things were noticed, right? I see a negative 1, I see a 4, a positive 4, and I see a positive 5. So out of the possible real solutions, out of the possible rational roots, I notice 3 that are on our list already. Okay? So let's start, I usually just start left to right. Let's start with the one that's all the way to the left and go from there. So I'm going to take this negative 1 here. It appears that it's a root. It was certainly on my list of possibles. Let's go check to make sure. That negative 1 root, let's start there. If I try a root of negative 1, that root of negative 1 goes on the outside. My polynomial coefficients go up top. And hopefully I take this out and I have no remainder, right? Because that's how we get good factoring work. There's no remainder. So bring the 1 down, multiply up, add down, multiply up, add down, multiply up. Oh, I must have done something wrong. What did I do? Oh! I multiplied wrong. See, there's my little check coming to my aid, right? I was getting a remainder, so I knew something was wrong. When I multiplied up, negative 1 times negative 9, that's positive 9, Mrs. Berger, not 10. Alright, add down, multiply up, and add down, and there's my no remainder. So I've taken that root out. That root worked. We have now confirmed that that is in fact a root. That's a nice clean root. I was right to notice that. Now, a couple different options. We can do this again, or we can take this quadratic that we just made for ourselves and factor it. Can we factor x squared minus 9x plus 20? We sure can. What two numbers multiply to positive 20 and add to negative 9? Well, negative 4 and negative 5. If we set those factors equal to 0 and solve, that means we have x equals 4 and x equals 5, which is what we thought we saw on the graph. We're just confirming that again. So our roots are 4, 5, and of course the negative 1 that we tried first. And you can put those in any order. Those are the roots. Now, we did not have to deploy quadratic formula on this one. These were nice and clean. We confirmed with factoring, so we didn't have to take any of those extreme measures. That won't always be the case, but I would certainly take advantage of any factoring that you can do so that you can keep your work clean and not have to deal with the quadratic formula. Now, speaking of which, you know we're going to throw quad formula at you. So let's take a look at number 8. We're going to start with the same steps. We're going to take a look at the possible rational roots and then see if we can see any of those on the graph. So let's talk about possibles. P over Q. There's P, there's Q. So P over Q possibilities are positive and negative. Well, the things that multiply to 2 are just 1 and 2. Over top of the things that multiply to 1 are just 1. So P over Q is just positive and negative 1 and 2. So if I look at my graph, I will expect to see either a positive 1, a negative 1, a positive 2, a negative 2. If there are any rational roots on here, that's going to be what they are. It's one or more of those. So let's go ahead and put this into our calculator and see what it says. Alright, notice here, again, what we were expecting, we were hoping for either a positive 1, a negative 1, a positive 2, or a negative 2. Did we find any of those? Well, if you look at this graph, it appears that there's a clean cut at positive 1. That looks fairly close to me. I'm thinking that that is a positive 1. But when I look back here at this root and this root, those are not cutting through at positive or negative 1 or positive or negative 2. Those are not right on those numbers. And yes, of course, you absolutely can use your second trace and go ahead and use the zeros function to notice that. But I will not accept decimal answers for these two roots, right? So you can confirm that this is a positive 1, but for these other two roots, I need you to get me simplest radical form for those roots, okay? So let's take and run with the one piece of information that we feel good about, and that positive 1 is a root, and then let's find what the exact form of those other two roots are. So remember, we can take that positive 1 root that we saw on the calculator straight out. We'll take the coefficients 1, -3, 0, and 2, because we don't have a linear term. Take the 1 down, multiply up, add down, multiply up, add down, multiply up, add down, and thank goodness we have no remainder. So the quadratic we have now is x squared minus 2x minus 2. Now we certainly would love it if this was factorable, because then we could factor it and set those factors equal to 0. X squared minus 2x minus 2. What multiplies to -2 and adds to -2? Hopefully you've thought about this long enough to realize nothing adds to -2 and multiplies to -2. So this is not factorable, so we will have to do the quadratic formula. Go ahead and renew what the quadratic formula is in your head. I'm going to fill those numbers in, so this is going to go to quad formula, and I'm going to enter -2 for b, plus and minus the square root of -2 squared minus 4 times a times c over 2a. That's 2 plus and minus the square root of 12 over 2. And this will simplify down to 2 plus and minus 2 square root of 3 over 2. And even further, this will simplify to 1 plus and minus the square root of 3. Okay, so we have just determined, and actually I shouldn't have put a box around that. I should have left room, because remember, that guy we found first, right? So those are our last two roots. Our first root was 1. So if we want to list all of the roots, we'll make sure we grab all of them. Because remember, how many were we looking for? The degree was 3, so we have 3 solutions, right? And so we found one of them on the calculator and with our possible rational roots. So we confirmed that one, and then we used quad formula to find the other two, 1 plus square root of 3 and 1 minus square root of 3. So those are your 3 solutions. If that went too fast for you, if you need to stop and study the work for a little bit, go ahead and pause the video. You will definitely need to demonstrate these skills on quizzes and tests. So we will give you a polynomial like this, and you'll need to use your skills to find all of the zeros. Okay? Alright, let's take a look at, we've got 2 more. Let's take a look at question number 9. Now, question number 9 is a cubic, so I'm expecting a total of 3 solutions. Let's figure out what my choices are. So if this is P and this is Q, P over Q must be plus and minus, let's see, what multiplies to 9? 1 and 9 and 3 times 3. Those are all the factors. And the only things that multiply to 1 are 1. So positive and -1, positive and -3, positive and -9. I'm going to go take a look at my calculator and see if I can confirm any of those. Let me go take a look at my calculator. And if I graph this, I'll take a look and see. Now again, I'm trying to see if there's anything happening at positive -1, positive -3, positive -9. Now this is interesting, and again, I'm looking for a total of 3 solutions. I see interactions in 2 places on the x-axis, and let's remember from our project unit about multiplicity. So I see an interaction at -3, that was certainly on my list of things to expect, and I see an interaction at -1. But remember those notes about multiplicity. The interaction at -3 is a bounce, so that has a multiplicity of 2. And the interaction at -1 is a cut through, so that has a multiplicity of 1. So that's all to say that I do only see 2 locations And so that leads me to believe, oh, I've got 2 roots here. Well, there's supposed to be a total of 3 solutions, so the third one must be imaginary. That's not actually the case here, though. The third one's not imaginary. The third one comes from the fact that this root happens twice because of this bounce, this multiplicity of 2. So this root happening twice counts for 2 roots. It's just happening at the same place. So 2 roots are happening at the same place, and one of them is here at the cut-through. Let's see how this plays out in the algebra, because it's not always going to be this nice and pretty, right? So let's see how this works out in the algebra. I'm going to start by taking this -1 root out, this singular -1 root out. Okay, I clearly see it. It was on my list of possibilities, so I'm going to go ahead and trial that. I'm going to take that -1 root that I saw on the graph, take that out and see what I'm left with. Let's grab our coefficients. Bring the 1 down, multiply up, add down, multiply up, add down, multiply up, add down. That's always a good sign when I have no remainder. So now I've got x squared plus xx plus 9. Can I factor this, or am I going to have to drag out the quadratic formula? I can factor this. I can factor this. So what numbers multiply to 9 and add to 6? Hopefully everybody's shouting. X plus 3 and x plus 3 are the factors of that. If I have x plus 3 and x plus 3, if I want the zeros that go along with those factors, we all know that x equal -3 and x equal -3. That is our last 2 solutions. So our first solution was that cut through at -1, and then we had our bounce at -3. So those are our 3 solutions. Those are our 3 zeros. And yes, you could have written the factorization as x plus 3 squared. There's our multiplicity of 2 happening, right? That's our bounce. So to list the roots, you would just say x equals -1 and x equals -3 double root. And you certainly could have said x equal -1, comma, -3, comma, -3. As long as you indicate that you found all 3 of them, it's just one of them is happening twice. Okay? Alright, now for the pièce de résistance. I'm sure I didn't say that correctly. I'm not a French teacher. And here's the big one. The big one is what I mean to say. So the big final one. Take a look at this one. This is a degree 5, right? It's a degree 5. We're looking for 5 solutions. And yes, you will probably see something like this on your homework. 5 solutions. Okay, where do we even start? Well, let's take a look at the possibles. I'm going to work up here. P over Q. What do we have for P over Q possibilities? What are all the things that multiply to 14? Well, there's certainly 1 and 14, 2 and 7, and I think that's all we have to choose from, right? And then Q is just that invisible 1. So our only options for rational roots are positive and -1, positive -2, positive -7, and positive -14. Let's go take a look at our graph and see if we can see any of those to just get us a starting spot. Okay, and be sure to put this in your calculator along with me. Don't just watch me do it. Make sure that you feel comfortable getting this into the calculator, get the exponents up there, use your caret. And let's go ahead and take a look at the graph now that we have it in there, and see if anything on our list, 1, 2, 7, 14, or -1, -2, -7, -14, pops up on this graph to at least get us started. That looks promising. That looks promising. Alright, now again, we have 5 total solutions. And right now, I think the graph is almost done drawing. Yep, there we go. The graph's done drawing, and I only see 2 locations, right? And I'm looking for 5 total solutions. But this is going to get me started. I see a root, a single root, at +2. That was definitely on my list of possibles, so that's promising. And it looks like I might have a double root at -1. So a -1 and a -1. So that looks promising as well. So I'm going to make use of all 3 of those roots to find all 5 of my total roots, okay? So it kind of doesn't matter where you start. I'm just going to go ahead and start with the +2 just for fun. I'm going to go ahead and try that too. So let's log here from the calculator. we saw a 2, a -1, -1, right? We saw a bounce at that -1. So from the calculator, we thought we saw that. Let's go ahead and confirm that those are in fact roots by taking them out one by one. So let's start with the 2, just because I chose to do the 2 first. Bring your coefficients. One down, and multiply up, add down, multiply up, add down, multiply up, add down, multiply up, add down, multiply up, add down. That's always promising when we see a 0. Alright, so now technically I could rewrite this answer as x to the 4th minus 2x cubed plus 10x minus, or plus 7, right? But that's actually not terribly helpful right at this time, because even rewriting that, I still need to take out the other 2 roots that I found on the calculator. So I am actually just going to say, you know what, I'm going to reuse this work that I've already done. That's my list of coefficients. Oops, sorry about that. That's my list of coefficients. I'm just going to reuse that list and do a new L chart. Right, instead of putting all the x to the 4ths and x to the 3rds and all that in there, why bother? I'm going to steal the coefficients again anyway. I'm going to have to make that 0 placeholder again anyway. Let me just reuse that and tackle, so I tackled the 2, let's tackle the first -1. Let's pull that one out next from the remaining polynomial. Bring the 1 down, multiply up, add down, multiply up, add down, multiply up, add down, multiply up, add down. And again, I breathe a sigh of relief because I have no remainder. So we've just confirmed that clearly 2 and -1 are roots. We thought we saw a double root at -1. So let's take another -1 out. And again, I could rewrite this as 1x to the 3rd minus 3x squared plus 3. You know, I could rewrite the whole thing, but why bother? I need to steal those coefficients anyway. So I'm just going to grab that work, make a new table, and take that other -1 root out for myself. Bring the 1 down, multiply up, add down, multiply up, add down, multiply up, add down. Now, I am out of, so I've taken care of all 3 of those, I'm out of roots, and I'm still looking for 5 total, right? But thank goodness, I am now down to, let me move this guy up here, I'm now down to something that is x squared minus 4x plus 7. I'm down to a quadratic, right? And that's always my goal. Get me to a quadratic that I can work with because I've got tools galore to find solutions for quadratics. My first goal is to try to factor this. Can I factor this? Is there anything that multiplies to 7 and adds to -4? I think about it, 1 and 7 are the only factors of 7, and they sure as heck not getting to me to -4, right? So factoring this is not going to work. I could certainly try completing the square. That's absolutely an option. If you're a completing the square person, go for it. We'll meet you at the end. Hopefully your answer is going to end up the same way. I'm going to go ahead and go with quadratic formula though. And like I said, completing the square is a fine method. So just meet us at the end. The quadratic formula people and the completing the square people should meet at the same place. So the last 2 solutions for this quintic function are going to be found with quad formula. -b plus and minus the square root of b squared minus 4ac over 2a. 4 plus and minus -12 over 2. Wow, not only do we have some square roots, we've got some imaginaries going on here, so definitely we're never going to factor this guy, right? So let's take a look here. We've got a negative in there, we've got a 4 sitting in there, so let's pull all of that out. 4 plus and minus 2i times the square root of 3 over 2. And then my last little bit of simplification, 2 plus and minus I times the square root of 3. Those are my last 2 roots. So, what are all 5 of the solutions of this quintic? 5 answers are x equals 2, -1. You could indicate in parentheses -1 as a double root. I'm just going to write it again. -1 and 2 plus and minus I times the square root of 3. Those are our last two. 2 plus I squared root of 3 and 2 minus I squared root of 3. Those are my 5 solutions to this quintic. You all should give yourselves a round of applause. I wish I had a soundtrack to give it to you for sticking in there. That's definitely the hardest part of these, is bringing all these rules together. You will have to demonstrate these, the division using the single root that you're given or that you see on the calculator, pulling that out, and then finding a tool, whether it be factoring or quad formula, to find the last ones. Okay? Alright, great job for hanging in there. Go ahead and attempt your homework and let your teachers know if you have any questions, especially before you take this quiz next class. Okay? Have a great time.